Yo, what is up, guys? Welcome back to the robotic arm videos. You've been waiting so long, almost a month, and I'm here, and I got some content for you. Let's get into it. The first thing that needed to happen was, of course, to finish the arm. It's not that I didn't like the forearm that I designed, it's just that it's f***ing hideous and I hated it, and I also printed it horribly. Also, I designed it backwards. So I got to work modeling a brand new forearm, a much better looking one. I printed it out, and I'll admit, reluctantly screwed it onto the arm. Now, I'm not sure why, but for some reason, I thought that putting on the Sharpie would make the arm look worse, and so I was saving it for last. However, I definitely didn't regret putting the forearm on. I finally had finished the arm, and damn was it sexy. With the arm finally done, I started writing some new code. This code was cleaner than my first code, and integrated all my functions into one neat package. Via the serial monitor, the arm asks the user for a number, each number corresponding to a different command. Pushing 1 displays all the possible commands. If you push 2, the arm will walk you through how to home it, and then it will home. Pressing 3 will invoke the angles function that we talked about last video, in which the user can enter their desired angles and the arm will move to those angles. After organizing the code, I went to send it to the arm, but I realized I couldn't do so without pressing the program button on the teensy, which was now buried deep inside my Apple I enclosure, named so for its apparent lack of repairability and accessibility. However, let's just say I found a way around that. After verifying that the reorganized code still worked as intended with my fancy new UI, I started working on what would happen if the user entered the number 4 into the serial. Remember, 1 was for commands, 2 was for homing, 3 was for angles, so naturally, 4 would invoke the dreaded inverse kinematic model function, allowing the user to manually test the kinematic model by entering a desired XYZ position into moving the Sharpie. Wait, XY what? I'm sure most of you are wondering, what the f is an inverse kinematic model? Well, I'm so glad you asked. Let's just say you want to draw a circle with your robot arm. Now, in order to do that, you need to be able to tell the arm to move the tip of the marker to the paper and then trace out a circular pattern right above the paper. Intuitively, when you draw, the kinematics, aka just the angles in between your joints, are automatically calculated by your body's big old meat computer up here. When you actually think about it, however, how the f does that work? It's not like you decided to move your elbow to the angle of 165.2 degrees, but that's, sure enough, what happened. Whether you realize it or not, the arm has to calculate those angles, and doing so by hand will result in a ton of manual labor that I'm not trying to do. So instead, I wrote some equations that take in a point, which is just a dot basically, and use the 3 numbers that define that dot to calculate the angle of the joints. The dot is defined by 3 numbers, as I said. It's horizontal, vertical, and up and down distance from the base of the arm. If we feed those numbers into my fancy pants trigonometry, which is basically just a fancy word for triangle math, we get the correct joint angles, and the arm can finally move the tip of the Sharpie to the desired point. Now, I scheduled an entire day to write this code, because I knew how awful it would be to do so. The math here is actually pretty similar to my V1 robotic arm, so if you want to learn about the math in depth, check out the video linked in the description with a timestamp to the mathematics portion. For about 2 hours, I couldn't get it working properly. So after combing through every equation I wrote, cross-referencing the results with Google, rewriting the equations with a million parentheses, to ensure correct operator precedence, I eventually stumbled upon the error, which ended up being a plus. That should have been a minus. Fun times! After that, though, the kinematics code for the arm's movement was working for about half the arm's range of motion. I was, however, experiencing a ton of accuracy issues, specifically with the base, which I was scared might be my code, until I realized that a part had failed on the robot. Thankfully, it was the smallest and easiest part to reprint. What a breath of fresh air. And while it was printing, I was able to finish up the kinematics code. Now, as I'm sure you remember, not earlier, I said in order to draw a circle, or really anything else for that matter, you need to know how to trace out that pattern on a piece of paper. Now, I'm sure the smarties out there have already figured out that if I simply turn the path into a bunch of dots, I can just tell the arm to move from one dot to another. This, by the way, is called interpolation, and trace out any pattern I want. So, all in all, a kinematic model is just a bunch of equations that I can take a point, put it through them, and it tells the arm what angles to move to. Alright then, all that theory sorted out, let's give it a shot. Step 1 is always to home the arm. So to get the arm to the homing position, move all the joints clockwise to where they're supposed to be, which they all are currently, and then just plug it in. It's plugged in now. So now I simply push 2 to activate the homing mode, send 2 to the arm. It receives that, it knows it's ready to home. You push enter, and the arm will home. Of course, we've all seen this before. The arm has now homed itself using the magnetic sensors. So now what I can do is I can enter kinematic mode by pushing 4 and enter. Now I'm going to give it an X, Y, and Z coordinate. I'm going to give it a coordinate of X being 70. So that means it will move, the tip of the arm will be 70 millimeters this way. Give it a Y coordinate of, let's just do 50, which means that the arm will move its tip 50 millimeters this way. Finally, a Z coordinate of 50, push enter. And sure enough, it will move the tip of the arm 50 millimeters above the table, 50 millimeters this way, and 70 millimeters this way. Now let's take a look at that. I'll measure up 50 millimeters, and as you'll be able to see, the tip of the Sharpie is approximately 50 millimeters off the table. Now, we can also check the other dimensions. The tip of the Sharpie should be 70 millimeters this way. You can see it's basically 70 millimeters that way. We can also test the x-axis, so go down to 50 millimeters, which is what we told it to do. And that seems to be a little less accurate, but you get the idea. It's just about 50 millimeters that way. So actually, that one's a bit screwed up. That's probably because of a homing inaccuracy, but we're getting there. Works great. Now, let's test it in interpolation mode, aka, let's draw some shit. So if you look at this right here, I told it to draw that. And let's see how close it gets. So I mean, the Z height control is not great. I don't think it's ever going to be great. That's just the nature of the beast. But if you look at this and where it drew it, it's remarkably similar to this. It's really not that far off. Okay, don't get me wrong, it's done a job, but hey, it's better than V1. At this point, I determined that the issue was bad Z height control. In layman's terms, it's hard to keep the Sharpie the same distance from the paper. You see, when a human draws, the pen rests on the paper, and only the X and Y movement is controlled by your arm. But remember when I said that the arm needs to know how to trace a circle above the paper? Well, I didn't say above for no reason. It literally has to hold it exactly X millimeters over the table, aka the height of whatever I'm drawing on, in order to draw. Now the problem with this is that even the smallest incorrectness in the angles of either the shoulder or elbow will muck this up bad. There are two ways to solve this problem. Better software and better hardware. I tried two things, one in each category. My software fix was to make the arm smoother. I thought that maybe the jittering movement was screwing up the actual versus software angle, so I thought if I could make the robot's joints all start and stop moving at the same time, I could make the entire movement smoother. To do this, I wrote some very complex even Boolean vector distribution code, which worked great once I got it working. Each joint started and stopped its movement at the same time, meaning the movement while drawing should be smoother and more consistent. Nice. My hardware fix was to make the Z height matter less, so I designed a spring-loaded Sharpie holder using a pen spring. Now here's how the arm drew after these two fixes. I can't really describe it. I drew a random shape and I'm trying to draw it, so let's try it again. It's drawing that! That's actually pretty good. Let's just try again. Yeah, well, it's drawing that. That's pretty good. This spring-loaded Sharpie works really well. Look at that. That's great. Look at it. You can actually see it working. So if I look, there you go. So the spring-loaded Sharpie works. So remember back when I said that a small part on the arm had failed? That was the small pulley. Now the small pulley is connected to the base motor, and it broke because the base motor got really hot. This problem didn't seem too bad at first, but unfortunately it was pretty bad. As I kept using the arm, the motor was so hot that it was cooking itself from the inside. Now the problem is replacing this motor is going to be 20 bucks on its own and probably take a day of wiring. But if I just replaced it, then guess what? It would overheat again, it would break itself again. So what I really would have had to do is buy a new motor, redesign the entire arm. It just would have been so much work. Honestly, too much work for me. And so the arm was starting to die, and unfortunately, so was my motivation for this project. In addition to that issue happening, the arm was really doing everything I wanted it to do. It was drawing way better than the version 1 was, and well, that was good enough for me. One cherry on top that really would have made this project great is a proper homing system. So I identified homing to be an issue on the V1. Obviously, calibrating the arm is very difficult to do, and that's why on this one I had the magnetic homing system. The magnetic homing system, however, it didn't work as well as I hoped. If I were to build this again, I would use physical limit switches, so instead of it stopping when it detects the magnet, it would stop when it hits a button, kind of like a 3D printer. Now, as promised, you can find the CAD files in the description below, but I don't think you should build this arm. I like the arm, okay? It's not that I don't like the arm, it's that this video is not designed as, you know, this video is not designed to just say, here, make this. This video is designed to inspire you to make your own arm and learn from my own mistakes so that you can make something better. I think that all it would really take is getting an arm with less backlash in the joints, better homing system, but you know, take some of my cues. I'll put my code in the description so you can use my math if you want. And improve on it. Make a better arm than I did. On some off chance, if one of you actually takes me up on that, comment below. I'd love to see where you go with this. So guys, that is all I have for you today. Thank you so much for watching through every last bit of this crazy montage. This was my biggest project ever. It took probably 100 hours combined to do everything. The video editing was kind of nuts. The arm was kind of nuts, just a little bit. And yeah, that's pretty much all I got. Like, subscribe, see you later.